And I don't know, maybe that's a better way to go. It's a little bit slower, perhaps. Whoops. Than looking at the pre-written notes. So anyway, these notes are pretty much the same ones we worked from last time, but I've extended them quite a lot to include more information. And I'm hoping that the thing that we're able to get today is, like, I'm thinking about what are the things about the untyped lambda calculus that we really kind of need to know to move on. And I think one of the standard things that's done is that we have all these different kind of notions of reduction. We have beta reduction, we have eta reduction, we have alpha conversion, we have equivalences, alpha equivalents, beta equivalents, eta equivalents. There's all these different kinds of notions, and I thought maybe I'll try to motivate why, and maybe I should start with that discussion at the very end if it came over. Let's see. Okay, no, yeah. So I mean, kind of the point is that we end up with a bunch of reduction relations and equivalences. So what's the point of that? Why are we doing that? It seems like maybe we're just going around in circles, kind of doing the same thing over and over again with a slightly different thing. But in the big picture, I mean, we kind of have syntactic equivalence, which, I probably should have started going from Hindley and Selden, but I don't know. I got immersed in Barendrecht because his definitions are pretty nice. He uses 3 bars. I think Hindley and Selden follow his lead and do the same thing, but it could have been maybe better to be looking at the Hindley and Selden PDF that is free out there. So we have to distinguish between, syntactic equivalence and kind of other kinds of equivalence. But in syntactic equivalence is between abstract syntax trees, and it basically says the trees are identical. But right away you get stuff like, okay, lambda x dot x is clearly not syntactically the same as lambda y dot y. So this is kind of disappointingly weak. This is a syntax tree that has an x in it, and this is a syntax tree that has a variable y in it, and x and y are different variables. So this is just not an identical tree. And so those two things are not syntactically equal. And so what we'd like to do is kind of like say, well, that's not, that distinguishes far too many terms from one another. And so then, and we're going to go over these definitions again and talk a little bit more about kind of the standard way of building these things. But so alpha equivalence is one where the named bound variable names are just not considered. And like I said, we're going to talk about De Bruyne indices, which allow us to do this by actually just getting rid of names completely. So we're talking about the alpha equivalence here, but in alpha equivalence, lambda x dot x is alpha equivalent to lambda y dot y because, and we'll see why later, we can rename this term to become that term. And but now if we look, we say something like, okay, and remember, like lambda x dot x is the identity function. No matter what argument you give it, you get back the argument. It takes in one argument, binds it to x, and just returns x, whatever's in x. So this, you know, clearly should be, we'd kind of like this to be the same as that. I mean, we would, what, why are these two things different? Well, they're just not alpha equivalent because there's no way to rename this term to be equal to that term. You have to actually do, like I did down here, you can do a step of beta reduction, and you can reduce lambda x dot x applied to lambda y dot y. Beta reduces to lambda y dot y. And lambda y dot y is alpha equivalent to the thing that we wanted it to be to up here, which is just a different version of the identity function. So alpha equivalence gets us closer to what we'd kind of like. I mean, what we would really like is an equivalence relation where every program that computes the same thing is in the equivalence relation with every other program that computes the same thing. Right? I mean, even in, if you think about, I don't know, think about your favorite programming language. There are an infinite number, accountably infinite number of programs. And think of your favorite program you ever wrote in your favorite programming language. There's a countably infinite number of equivalent programs, right? Just suppose the variable X occurs in your program somewhere. You can make a new program by inserting an assignment that says, oh, X gets the value of X. That doesn't change the outcome of the program, but it's a different syntactic object, right? Your program now has one more line than it did before. And so it's the same thing with lambda terms. I mean, we can insert all kinds of crazy applications of the identity function to just make a program bigger and bigger and bigger, but they all compute the same thing. So beta reduction defines what it means to compute with in the lambda calculus. We'll go over that again. We're going to go over all these things again so that so that you get it more secure in your brain, because these are fundamental ideas in untyped and typed. So beta reduction is what we would really like. We would like to be able to, two terms are beta equivalent if they compute the same thing, on all inputs. They're the same program. But the problem is that this is too strong of an equivalence, because lambda terms are Turing complete. There can be no algorithm to decide. I give you two lambda terms and I say, okay, run them on your algorithm and tell me whether they're beta equivalent or not. Oh, and I should have one line there. He distinguishes between kind of the syntactic based idea of equivalence and more of a computation based equivalent. So, he uses equal sub beta instead of triple equal sub beta. Oh, and I guess I didn't write down eta reduction, but we're going to talk about that. I mean, eta reduction is just the one that, well, we'll go up and look at that. That's weaker than beta reduction, but it allows us to simplify some terms. So kind of like in the end of the last lecture when I was, like didn't know the proof, and then I recognized, I need to apply eta reduction here. Eta reduction allows you to get back, get some things to look equivalent that are eta equivalent. So anyway, I don't know. Are there any questions on this? I should have had eta reduction in between alpha and beta. It's weaker. And it's really also just a syntactic property. I mean, no questions. Come on. I don't believe it. Am I like too harsh if you ask a question? All right. So let's go back up and look at all these different kinds of equivalences. And so the first thing to remember is kind of the syntax. Okay, we only have three things. Well, and if we want, we can add parentheses where we like, but we, you know, as far as syntax trees go, we don't need this constructor because we can, you know, this allows us in the linear notation to balance things in certain ways that we can't do unless we have parentheses. But in the tree, we can always build the tree to be the one that we want without using parentheses. So that's just a property of syntax and abstract syntax trees. So we have variables, apply m to n, and lambda x dot m. So I thought maybe if, you know, it seemed like if you haven't seen this kind of like BNF description before, this is an alternative way to give this definition. So you say, okay, look, we have some set of variables, let's say v0, v1, dot, dot, dot. And we've got symbols like lambda and left paren and dot and right paren. Then the set of lambda terms is the least set satisfying the following conditions. Now, the least set condition is in there because up here we say m, and m must have been previously constructed. And the least set ensures that you never put anything in there that doesn't get built up from the bottom. So here's the rules for constructing all the lambda terms. It says, okay, variables are in the lambda terms. And so x is in this set v0, v1, dot, dot, dot. So x is a variable. If x is a variable, then it's in lambda terms. If m is a lambda term, then lambda x dot m is a lambda term. And if m and n are lambda terms, then the application of m to m is a lambda term. So I thought maybe, you know, I don't know, if you were not able to think about this because it's new, then maybe this helps. You're building this set, lambda. So, you know, the conventions are that MM, you know, primed and are arbitrary lambda terms. X, Y, Z, and W denote arbitrary variables. So even though in our meta language, when we're talking about lambda terms, we use, you know, X, Y, Z, and W, really they have to be, those are things that range over variables. And this is important, that the symbol triple equivalence denotes syntactic equality, because, and I'm not sure I've been consistent in rewriting down here substitution using that syntactic equality. Yeah. Well, I'm using like a pattern matching here. Go ahead.
Doesn't this also mean that you could have equality because things are equal parse trees?
That's exactly what it means. They're equal, the abstract syntax trees. Yes. And this is
right. And can you also have equality when you have not just equal parse trees, but there is some transformation on those equal parse trees that allows you to get from one to the other that does not change the value that it produces.
Right. That's exactly what these
That's
different.
the MN.
Yeah, that's the
And
that's alpha equivalence does that, and beta equivalence does that. Well, it transforms it to a different parse tree. These transform to different parse trees, although this one, the trees are the same structure, they just have variable namings in them that are different. And this one eliminates some unnecessary structure. And this one actually does some computation, but the thing that you get is equivalent to the original program. It will compute the original thing. So yeah, that's the idea of all these different things here. Is that good?
that's good. Yeah.
Yeah. So when you say M is syntactically identical, you mean the parse tree is identical at this point. And it means that M and M have identical abstract syntax trees with identical variables at the leaves. So here's some examples of a couple of abstract syntax tree, like lambda x dot x becomes lambda xx, and lambda xy applied lambda. Okay, so here's a convention. Lambda, if you write down a whole bunch of variables and then a dot and then some term, that's the same as writing down lambda x1 dot, lambda x2 dot, lambda xn dot m. So you can kind of glue together. You don't have, you can write this down as lambda x y y x instead of writing it as lambda x dot lambda y dot y x. They're identical. So that's another one of these conventions here. But when we look at the parse tree, it looks like this. Lambda x has one subterm, which is the lambda y term, which has two subterms in the body, which is y applied to x. Oh, I drew that wrong, really. I need a symbol for apply. So lambda y should have a line down from it, and the y and x should be above an apply term. Okay? Maybe, should I redraw this in the correct way? Anyone? All right, I think I'm going to. I don't know. I'm not sure why I'm thinking this is important. If I can get out of here, come on, stop share. I just want to go to the whiteboard. Okay. Okay. You have to speak up instead of chat, because for some reason I can't really keep track of what's going on. I can't see the chat.
If redrawing the diagram will help, or if the original diagram is wrong, then yes, can you redraw it?
Yes, please? Right. Yeah, I'm going to. So what was the term? The term was lambda x y dot yx. Oh, here's my problem. I'm like, why is this so painful? Because I'm using my mouse instead of my tablet. Okay. So lambda x, whoops, y dot yx. Well, and the one thing I said was this is the same as lambda x dot lambda y dot yx. But the tree structure of this is lambda, and somewhere this node is labeled by an x so that you can check things. And then this goes down to a node labeled by lambda y. And then that has only one subtree. And then this is like apply. and the left thing is a y, and the right thing is, so this is like apply y to x. Okay? So now let me go back to this. Now, the free variables, we went over this last time, but you just calculate, you just, the free variables, you just union them together for an application. X is free if you encounter it just standing alone. And otherwise, this is the only one. You get the free variables of the body of a lambda expression and to remove the bound variable name X from that set. And we did a calculation last time that showed that the free variables in here are just the free variable z. Another way to think of it is that you can, if you have an abstract syntax tree, like suppose I take this, you can travel up the tree, and if you get to the top and you've never seen a lambda labeled with that, like if this was a z, for example, I could go up here and I go, okay, am I a y? No, I'm a z. Okay, I go up here. Am I a x? No, I'm a z. Okay, I'm free. But if you go up, like here, from here, y, and you reach that, this lambda is tagged with a y, and so you're bound. And this one here, you go up and up. Nope, I'm not y, but yep, I'm x. So all the variables in this, the body of this term are bound. And if there's no free variables, then we frequently refer to the term as a combinator. Okay, so capture avoiding substitution, we said last time, is kind of this tricky sort of thing. And there's two rules for variables. And here's where I could have used equals. Oh, here, this should be equals without the little funny brackets overward. This is oftentimes what I use for syntactic identity. So this should really be equals. But if I'm replacing x, all free occurrences of x by n in the term that's x, is x free in itself? Yeah, the free variables told us it's free. So that means, yeah, go ahead and do the replacement. Now, the interesting thing is that this is the only place in the entire definition where anything gets substituted when you get to a variable. And then, if you're looking, if you're saying, I want to replace all free x's in y by n, well, y is not equal to x. They're syntactically different variables. So then we just say, don't do anything. You just return y. If you want to do it if you want to replace all x free occurrences of x in M1 applied to M2 by n, you can just go ahead and recurse down. You apply the substitution in the M1, and then you apply the substitution in M2, and then because they're adjacent, they get applied, the application is rebuilt. So the result of this is an application of this term with that substitution done to this term with that substitution done. Now, this one is a kind of, actually, in a way, the next two are simplifying. We really only need rule 3, but it's the most complicated one, and it's also computationally expensive. So this one's easy. If I'm replacing all free x's in lambda x dot m by n, if you look at the definition of free variables, x is going to be the one that is not going to be in the free variables. So there is no free occurrence. There is no free occurrence of x, of x in here because x is not free in here. So that means you might as well stop, because the meaning of this capture avoiding a substitution is replace free variables. So you could be coming down through some giant tree and you're saying, and you hit this one and you go like, oh, nothing to do. I don't have this tree here. It could be, huge. So this is a bit, this is kind of cuts off the search for variables to replace by noticing that X cannot appear free anywhere in here. Now, what you kind of want to do, the naive thing to do, is to just go ahead and say, okay, rewrite, I'm replacing all free occurrences of X by N in lambda y dot M. And so you just say, okay, that's the term, lambda y dot, and now recursively go down inside of M and replace all the X's by N. But if Y is in the free variables of N and Y is in, and X is in M, then, this is going to cause a variable capture. So the case where you can avoid all this is you basically rename Y to Z, and then you go down in the body M and you replace all the old Y's by the new Z, and then you take that thing and you just go ahead and replace X by N. Now, this definition is the full definition of capture avoiding substitution, but it's a little bit different from Pierce because Pierce, and I've sort of discussed it down below, uses what Barendrecht calls the variable convention. And basically what it means is that it's possible, like if I'm proving a theorem and I know, okay, I'm going to use terms, M, M1, N1, here's a collection of terms that are used in the description of this theorem. I can go and make sure that every lambda has a completely unique name. So I can kind of like rename everything before I start so that you never would run into that condition that we're looking at here where Y is in the free variables of N, because Y would have been a variable name like that occurred nowhere, anywhere else in any of the terms. So you'd never run into this. And so it's kind of like what Pierce depends on and what Barendrecht depends on is that when you write down the theorem, you just assume that any terms that in there with bound variables, with lambdas, have different names from any other variable occurring anywhere in the statement of the theorem. But that kind of avoids, that means you got this pre-computation thing to do. If you want to go ahead and use the kind of the naive one, you can always use this rule, even though it would, well, no, this would never happen. You would never be replacing X where X is not some completely different variable. So rule 2 would always work because it would never be the case that X is equal to something you're substituting. And it would never be the case that Y, which is this one, would occur free in there. So this rule is the naive rule, but it misses this case. And we went over this last time, but here's a case where the renaming occurs. So it turns out that capture avoiding substitution is kind of the basis of the method of computation in the Lambda calculus. And I remember somebody at one time when I was, Bill, what's his name? Bill Well, I can't remember his last name. Anyway, this guy told me, he said, isn't it shocking that capture avoiding substitution is like the lambda calculus with beta reduction is Turing complete? It's kind of shocking that this process of doing substitution in a term is a kind of a computationally, I don't know, full operation. It's enough using capture avoiding substitution as your method of computation to describe all programs. Does anyone else find that surprising? I don't know. I did. Feel free to talk up. I mean, there's not enough of us here. Interrupt me.
Yeah, I do find it surprising because I don't understand why it is sufficient. I mean, I've read that before and I went, okay, it is,
Mm-hmm.
but I don't get it.
Well, I
Yeah,
know
it's pretty wild.
It's kind of a puzzle, but I guess then, you know, I mean, the reason we could show why, but it doesn't really show why, is that we can do a proof where we could encode. So, I mean, what does it mean to be Turing equivalent? It means everything that could be computed by Turing machine can be computed by a lambda calculus term, and everything that can be computed by a lambda calculus term can be computed by a Turing machine. And Turing did the prove the two are equivalent, and then we have the Church-Turing thesis, which says, okay, everything that can be computed in principle by Turing machine. So, but that proof is kind of simple, really. In a way, you write a lambda term, and it's, you know, it's kind of big and complicated, but it can simulate any Turing machine. And so then you give it as input an encoding of the Turing machine, and it'll do whatever the Turing machine does. And at the end, you've simulated every possible Turing machine because you can simulate the universal Turing machine by a lambda term. And then going the other way, you can write a Turing machine that takes on its tape an encoding of a lambda term and does whatever the lambda term should do by beta reduction. And so now the two are the same, but you're right. It doesn't, I don't think that really kind of gives you, I don't know, doesn't give you maybe the guts of why this one operation is enough. I mean, I guess then the other argument is, you know, we've seen that you can encode from reading Pierce. You can encode arithmetic in here. You can encode Booleans in here. So you can kind of encode all functional programs, and functions reduce by this operation. So maybe that's it. But it is kind of surprising if you just think about that this definition, even though it's a little complicated, is enough to capture everything that's possibly computable because of beta reduction. So I don't know, any other comments or thoughts on that? Okay. So beta reduction is
beta reduction, oh, sorry.
Go ahead.
So is beta reduction considered the strongest form of induction that we have available to us then? Is that correct? Like,
Well,
we touched on a little bit some like weaker types, but like, is beta reduction the go-to then because of that?
well, beta reduction is how you do one step of computation in the lambda calculus. So it's not really an induction as it is what we call actually a reduction, because you're computing with this. Now, okay, so this is what it means. Here's a term that is a lambda term applied to some other term. M and M are arbitrary terms, but I at least have a template that looks like this. I could draw, you know, a syntax tree that shows you the top level of this template if I could. Why won't it let me get out of here? I don't get it. There, it takes so long. Okay, so I could stop share. And then I can go back to the whiteboard. And so, you know, we've got something that looks like, whoops. Now what happened to my Wacom? Come on. Seriously? That is so weird. My mouse works, but my tablet no longer works. How can that be? It just worked a minute ago. All right. All right. Well, let me try and draw it with my mouse. This is ridiculous, but okay. So I've got something like lambda x, and then underneath here, I have this syntax tree. I'm trying to draw like a triangle under there. So this is the body of this. This is M. That's the body of that. And this is applied. Oh, come on. What is going on? Oh, that's so, anyway. Okay, 2 N. So this is kind of what the shape of a redux is. And then what it beta reduces to is the body M. And there may be, and remember, variables will always occur as leaves of a term tree. And what happens over here is wherever there was an X, now I plug in one of these N's. So that's kind of like from the tree level, that's what beta reduction looks like. I've got a lambda term applied to some arbitrary term. And what happens after I do beta reduction is I have the body of the lambda term, and wherever there was an X at a leaf of the tree, the syntax tree for M, there's now an N. So I don't know if that like visual thing helps.
It actually does. Thank you.
Aha, maybe I can find, where's my Wacom tablet? I don't know, maybe it's out of power. All right, I might plug it in. Oh, Jesus. You know what? So embarrassing. I'm using my Apple Pencil on my Wacom tablet. No wonder it didn't work. Okay, so can you see the notes again?
Yes.
Yes.
Okay. All right, so beta reduction is this, and when we look at like a tree, like I just drew, then you know you maybe get an idea of what this looks like. And this is called the redex, and this is called the contractum. I don't know. You know. So now, the thing is that this really only describes this relationship between pairs of terms where the top level term has the structure that I just drew. It doesn't allow you to go down inside of a term and do a beta reduction. And that's what this does. This is building, I mean, it says, okay, this arrow beta, single arrow beta, is compatible, and you can look on page 50 of Baron Direct. It's compatible with Lambda when we describe this relation, and this relation says, okay, all the terms, you know, this term is in the relation of beta reduction with that term. And then if M beta reduces to M prime, then Z applied to M beta reduces to Z applied to M prime. And M applied to M prime beta reduces, if M beta reduces to M prime, then I can do an application on the right to both of those terms. And if M beta reduces to M prime, then I can wrap them both in a lambda, and this one will reduce to that one. So now I am glad I got that figured out the tablet, because this is kind of like the standard way to take a relation defined on terms and let you build a new relation that lets you kind of apply this anywhere. So, you know, suppose that I had, like, I don't know, let's say I have, like, I don't know, lambda x dot lambda y, well, or lambda x dot x applied to y applied to x applied to whatever, z, let's say. Okay, so what does this look like? This looks like an apt term with a z. And then over here, I've got a lambda x. And then down below that, I've got a apt term of a lambda x applied to y, except that then this is, oh, it goes the other way, right? I need, you know, this term here is what? It's lambda x dot x applied to y applied to z, because function application associates to the left. So I needed to do this a little bit different. I need to put the other apply here, and now I have lambda x applied to y, and then the result of that gets applied to z. I'm sorry, x. What did I do? That should be an x. Come on, you guys should be like screaming at me. What are you talking about? So this thing here is this, and that's represented below here. That's an x. So now if you look at this tree, there is a top level redex here, right? Where this is of the right form to be a redex, but so is this. And what I would like to be able to do is to say, okay, I could either reduce this or I could reduce this. And that's what that relation that we just built does, because it says, so I can do lambda x dot x applied to y, beta reduces to just y. So this thing, I want it to beta reduce to like that. But it's also possible, there really is there no way to grab and copy something in here? Okay. So, but all right, I can erase this stuff on the left side because the trees are more important anyway. But it's also the case, so maybe I should label them with different things, with different colors. So this one is orange, and then that means that the one that we already did was orange. But if I do the yellow one, I get a different tree. And so now I take this tree down here and replace all free occurrences of x by z. So I take, this goes to this, and I replace free occurrences of x by z. And now I still have the orange one here is now the root. Did I do something wrong there? Yes, that's not right.
Yes, you've got a mistake, but at a higher level, basically what you're saying is that because we have choices in the order in which we evaluate things, we can end up with different trees, and it's very difficult to do beta reduction and match trees.
What did I do wrong here, though? I want to apply z, and I want to take this tree here, and I want to replace all the free x's by z. So I got that right. Oh, it's just that I should have, this is what I wanted to do. This one still remains. There's still a redex in this term. There's a redex. And so now I can do the orange one. And now I can say, okay, replace all the replace this by y. And so I end up with I wanted that to be black. Okay. So what do I end up with? I have the body, which is lambda. So I end up with a z here. That doesn't change. And then this redex becomes just y.
Yeah, but isn't that also true on the other side?
And
Where if
it
you,
is
since you,
on the other side where now I still have my, I did the orange first, which collapsed this to Y, right? So this whole thing here became Y. And now I can do the yellow one from here, and it's too bad I can't make this thing sort of dynamically wider. But if I do the yellow, the yellow one remains, which is still the top level. And so I can go in here and I can say, okay, take the body and replace all free occurrences of X by Z. So this becomes YZ. You know, maybe we've almost been going an hour, which is fine. I mean, maybe I should write this out in linear form. If I could remember what is the term. I wish I could scroll. All right. Lambda X, what was the original term? Somebody help me here. Lambda X dot lambda Y dot Y. Oh, lambda X dot X applied to Y applied to X. And then this whole thing applied to Z. And so the idea was that there's this redex. Is that the one I labeled yellow? Yes, the top one was yellow and the bottom one was orange. And then there's this redex. And so we can go either way. We can do, you know, if we start with the orange one, get back lambda X dot, whoops, sorry. I'm sorry, we get lambda X dot, that becomes a Y applied to X, applied to Z. And now I still have the yellow one in there, kind of the top. This is a redex. And so now I can do the yellow one and I get Y applied to Z. Or I could have done in this linear format. I mean, I don't know, maybe this is a waste of time, but and so if I did the yellow one first, I take the body and I got lambda X dot X and Y, and there's one free X there that becomes Z. And now I still have the, this is still the same orange redex. And now, so now I do the orange one. And I get back YZ. So I guess there one question you might have, is it a coincidence that we ended up with the same answer? And this is one of the deepest and most beautiful properties about the lambda calculus, is that if so, terms that have no redexes, beta redexes in them are called normal forms, beta normal form. And so, you know, this and this are in beta normal form. There's nothing left to do. There's no computation left to do. And it turns out that if it's possible to reduce this to a beta normal form, you can go another path and you'll be reduced to the same beta normal form. It's always possible to kind of redirect. Now, we could have this really horrible thing in here. And in a way, this is why lambda calculus is, you know, I could say like, okay, this omega term is lambda x dot xx applied to lambda x dot xx. And what is it beta reduced to? It beta reduces to itself. So this thing just has it never has a normal form. I just should say has no normal form, not never. But I mean, no matter how much you reduce it, you'll never get to a normal form. So suppose I did something like, you know, like, okay, lambda x dot lambda y dot x applied to z applied to omega. You know, I could always kind of make a bad choice and end up with the same term again because I chose to go down in here and reduce that one redex. So you could have an infinite path of reduction in this term. So, you know, that doesn't look good. So if we end up with the same term, I'm going to say, no, don't do it. But we could say lambda x dot lambda y dot x applied to z applied to omega does reduce to lambda y dot z applied to omega, which beta reduces to z. And this ability to kind of like steer the reduction path back to the normal form is always possible if there is a normal form. We're going to talk about that. And now we've been going for an hour. Do people want to take a little break or no?
Five minutes would be handy. Thank you.
Okay.
Yeah, a break would
Yeah.
be nice.
I think
Okay,
5
good.
minutes is essential.
Okay. We're going to take a little 5-minute break. We'll be back at, let's say, 2:10. Philip, did you get
I'm
your
clicking my mic. Yes, sir.
Interfolio packet together for your review?
I don't know what I'm supposed to do for these things. Are you kidding? I put some stuff in it.
Okay, good. Yeah. I know.
Um,
I was up till 11 last night doing mine. I'm like, oh my God. I was ready to just say, you know what? Fire me if I don't do it. But I don't know. It's not helpful.
okay, I am at the same point. It's like, well, I put some stuff in it, and if you don't like it, so who cares?
Right. I mean,
Okay.
yeah, but it's just so annoying. They just keep adding on more and more levels of,
Yeah, at least this year the software worked right for me. Last year, the stupid software didn't even work.
Right, locked you out and stuff like that. Anyway.
Well, it didn't just lock me out. I mean, I put something in that was wrong, and then there was no way to change it.
Yeah, right.
It's like, well, thanks. I just made a mistake. I can't edit it. No, you can't edit it. This year, at least I could put stuff in without it like goofing up. But yeah,
Okay. Anyway, all right. I'm gonna go back to the. I was trying to figure out. Let's see. How come there? I just don't get it that I don't have like some kind of whiteboard app that I can run on my Linux box. All right. Okay, so let's go back. Well, I mean, maybe I should. I got to go back to this. So the question is, like, we were looking at this relation here, which I claimed what the effect of this was to allow us to do reduction down inside of a term, not just at the top level. And so maybe I can I mean, the fact that I can't cut and paste this onto my whiteboard, I mean, all that stuff is just. So let me try to show you that how this definition works for that. So I don't know, suppose that I have some term like this one here. And I want to do the inner one. So lambda x, x, y. All right, let's see if I can. Whoops. What was it? Oh, who cares? Okay. Now, those rules would let me say, for example, lambda y dot y applied to x, beta reduces to x. And then I have a rule that says, so one of the rules is that if m beta reduces to m prime, then Now, what do I want to do here? I want to apply a z on then mz beta reduces to m prime z. So I can rewrite this one now as lambda y dot y applied to x. And now I can put any term on the right that I want. So I'm going to put a z over there. And so that reduces to xz. Now, unfortunately, this z is a z. Maybe I should, that's potentially confusing. All right, this is like, you know, for any n. Oh, God. So this rule, choose m n to be z. And so I applied the z here, and maybe I shouldn't have put those parentheses in there. Just took this term and applied it to z, and I can take the x and apply it to z. And now there's another rule that says, so I can build back up to what I need to be at. There's another rule that says, oh, you can wrap a lambda x around any term. So lambda x dot lambda y dot y applied to x applied to z reduces to lambda x dot x applied to z. So that's another one of these rules. It says, you know, if m beta reduces to m prime, then lambda x dot m beta reduces to lambda x dot m prime. I mean, I can write this as like implies. This is how it's written in the rule x. Beta reduces to lambda x dot m prime. So that's how I'm going from here to here. And then there's another rule that says, well, this one again, I can take this thing and apply it to y. And so I get lambda x dot lambda y dot x z applied to y. Beta reduces to lambda x dot xz applied to y. So what this did was, hopefully, if I've done this right, is this read x reduces to this. So here's that, and here's the read x that I had. I applied it to z. And then now I wrapped a lambda around it. So now I get to this from wrapping a lambda around that whole thing. And now that, you know, you can still, I don't know what I'm circling actually anymore. Oh, I missed a paren there, right? Because this is lambda y. So lambda y dot, yeah, okay, reduces to lambda x dot xc. And now I can apply a y on the right. So I'm missing a paren here. Oh, no, it's in here. That's the one that I'm missing. I'm copying that erroneous missing one. Okay. So if I go and look back on the previous, so these were the two rules that we used. And if I go look on the previous page, we'll see lambda x dot lambda y. You can see that that reduces to this when you choose, and I forget, that's the orange one, I guess. I should have colored in orange. This one reduces to this. Oh, reduces to this. I started with a different thing, but you can still see in here kind of like the original redex that I started with. Here it is. And here it is. And what these rules allow me to do is to build up the context around them to get back up, build back up to the original term that I started with. So I don't know, does anybody see, is there like an error in here? Let me just see, lambda x dot lambda y dot y applied to x applied to z applied to y. So that beta reduces to, by doing this inner one, lambda x dot, the inner one reduces to just x z, and I still have that applied to y. And so that is exactly what we have here. By going down and just allowing you to pluck out this internal one, this internal, well, I wanted a color, the internal redex, and reduce that. And so you can reduce anywhere in a term if there's a redex. Questions? No question. Comments? All right, let's go back. So this one now, it turns out that you can do this kind of construction with any relation on terms, and you end up building a compatible relation that lets you apply that transformation anywhere. And then now this is from Pierce's way of doing it, and this is an absolutely standard way of building the reflexive transitive closure of a relation, but I'll show you two ways to do it. So this is kind of like the ordinary computational way. And so first you say, okay, let me define this arrow sub beta with a superscript with a number on it, which indicates how many steps of beta reduction it took to get from one place to another. And so that's what this relation is going to be. It's going to be the k-step beta reduction. And so m beta reduces to m in 0 steps. So with no steps, you get back to yourself. And then m beta reduces to n in k plus 1 steps if there's some m prime that m beta reduces to m prime in 1 step. That's this relation that we defined up here. And m prime beta reduces to in k steps to n. So that's one less step. So we've added one actual concrete step. We said, oh yeah, I can go from here to M prime. Okay, and then it has to be the case that M prime leads to N. And so now I'm defining inductively on K here to build this relation by sort of making each time one more step concrete. And so then you can use this to build the star relation of beta, which is the reflexive transitive closure of beta reduction. And so you can say M beta reduces to N in 0 or more steps if there is a K, which is a natural number, such that M beta reduces to N in K steps. So this is disallowing infinitely long chains in this star relation. It's a finite number of steps. And then once you have that, you can define beta equivalent. So like, I don't know, anyone have any questions? Go ahead, Phil.
I have a comment.
Yeah.
You know, it all seems kind of abstract, but I will tell people that I have actually used this in building compiler stuff.
There you go.
Okay, at least once in the real world. So this is not just, you know, kind of like, oh, it's just this reduction and we can do these transforms. There really is, like, down in the guts of compilers, stuff like this that depends on these things.
Yeah. So, I mean, no, there's no question. This is, well, and it's concrete. I don't know, Keegan, which evaluator did you say you were using yesterday? You told me, I forgot. Can you put a link to it in the chat if you're awake?
Yeah, I can do that.
Oh, you're awake. Okay, good. Yeah, put a link to this. So, I mean, there is a nice Lambda term evaluator that, I don't know, I've played with it a while ago, and this guy at, well, he graduated from Stanford. Now he's out in the real world, but he builds all these kinds of things. And it's a very, you know, it's a kind of a pretty nice Lambda evaluator. If you want to try some of these things, you can actually, you know, try doing beta reduction and stuff. Okay, so look, this is beta reduction. Now, the value of beta equivalence is, in the beginning of the class, I was pointing out that you know, this is the one we'd really like. This is really saying two programs are equivalent. So beta equivalence is kind of really the strong one that we want, but it's also too strong. There's no algorithm that tells me if I give it two arbitrary beta terms, can you reduce one to the other? So there's heuristics for doing it, but there were no algorithms. All right, so the other important one is equivalence, and they say like modulo or up to renaming of bound variables. And so, you know, like lambda x, lambda y, xy is not, that should be a third, syntactically equal to lambda y dot lambda x yx. Those things are not, and they're even more complicated, but they are alpha equivalent, because if I rename, you know, you got to do a trick in here, and that's what substitution will help you with. Here's the definition of alpha equivalence. And we say, now, why do I have 3 lines here for alpha equivalence? Is because Barendrecht and Pierce kind of think of this as almost being like magic that's built in. If you needed to do an alpha conversion on a term to make it so that you don't have to have that complicated capture avoiding substitution algorithm. This one, if you always want to be able to use rule 2 for lambda terms, then you have to have some magic that automatically converts everything to be alpha equivalent terms, but not how come it won't let me go to I wanted to zoom in so I could read that note. The alpha equivalent, but no bound variable names are the same in any binding. So anyway, here's how you can, here's the definition of alpha equivalence, and it gives you the way to kind of compute alpha equivalence. It says, look, every term is alpha equivalent to itself. Well, that's perfectly sensible. If M is alpha equivalent to N, then N better be alpha equivalent to M. That's just adding, all equivalence relations are reflexive, symmetric, and transitive. So this is just adding symmetry. This one is just adding transitivity. If M is equivalent to N bar and N bar is equivalent to N, then M better be equivalent to N. So you can go sort of through, and this is transitivity. This one is saying, if M is equivalent to M prime and N, this is kind of the compatibility part, then Mn is alpha equivalent to M prime N prime. And that's because this one is the same as that by alpha equivalence. This one is the same as that by alpha equivalence. You can just put them together with an application. This one is more compatibility. It says you can wrap a lambda around them. But note that the variable has to be the same on each. And now this one is the one where you finally get to do some work. Like if you wanted to show that lambda x dot m was alpha equivalent to lambda y dot n, then what you got to do is pick a fresh variable z and rename all the x's in m by z, and rename all the y's in n by z, and that will give you two things that now you can go on and use the rest definition to show if they're alpha equivalent. Now, sometimes it helps to write this down in a rule-based form instead of using this. You say like, okay, it's just an axiom that every variable is alpha equivalent, or every term is alpha equivalent to itself. And if n is alpha equivalent to m, then m is alpha equivalent to n. If you could show this, then you got this. So that kind of lets you turn it around, right? That's kind of like if you think, well, you might think of it as a one in beta, in the case of beta reduction anyway, this is like saying you could take a backwards beta step. Here you're saying, look, if I want to show that m is alpha equivalent to n, you could show that m is alpha equivalent to n hat, and n hat's alpha equivalent to n, and then you've done it. Or, you know, you could show that m is equivalent to m prime and n is equivalent to n prime, and then you've shown this. Now, this rule here, which unfortunately, but I think you can still read it, says, look, if you want to show that lambda x dot m is alpha equivalent to lambda x dot n, just show that m is alpha equivalent to n. That's when the variables, the bound variable names are the same. You just can recurse, you can just go down into the bodies and check them. Or if it's more complicated, you've got a lambda x dot m and you're trying to show that that's alpha equivalent to a lambda y dot n. Well, pick a fresh z, a z, which is a variable that doesn't, it's not x, it's not y, it does not occur free in m, does not occur free in n. And now just go check the body of m with all the x's renamed to z, and go check the body of n with all the y's renamed to z. And this rule here, this rule 5, the 3, 4, 5, 6, this rule 5 is actually not necessary. In fact, we could prove it as a derived rule using the other rules and some theorems about capture avoiding substitution. So rule 5 is not necessary. It's simply an optimization. But here's how you could use this, like to show back in this original thing, to show that this is alpha equivalent to that. You write it down and you say, okay, to show it's alpha equivalent, all right, there's one that says I can pull off. So now I've got an X and I've got a Y. So that means I'm using rule 6 here. And Z is the fresh variable. So I go down in here and I rename all the free X's by Z. And I go down in here and I rename all the free Y's by Z. And I get this is equal to this. And I apply that same rule 6 again. And this time I choose a fresh variable. Why? I know it's like not a hard choice. I'm trying to show one lambda terms equal to another, and the bound variable name is different. There's only one rule that applies. So I go down in here and I say, okay, choose W as my fresh variable name. And this is the result of replacing all the Y's, the free Y's in here by W, I get ZW. And when I replace all the free X's in here by W, I get ZW. And actually, I guess I could have stopped there by this rule number 1, but I broke apart the application and then used rule number 1. So these are pretty easy, and you could easily write a program to do alpha conversion to check. This is a decidable. There is an algorithm. If I give you 2 terms, you can check whether they're equivalent. Under alpha conversion. Now, here I say, look, note Pierce considers this to be automatic. And similarly, Barendrecht does also. He adopts this bit of magic by his variable convention. And here it is. He says, convention, terms that are alpha congruent are identified. So we will write lambda x dot x is syntactically identical to lambda y dot y. And he doesn't add the alpha on here. He just considers that syntactic identity. And so he says, if M1 dot 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 M occur in a certain mathematical context, for example, a definition or proof, etc., then in these terms, all bound variables are chosen to be different from the free variables. So this kind of magic happens up front, but to do it, you would have to follow this. And then his moral is using conventions 2.1.2, which is the convention, and then the variable convention 2.113, one can work with lambda terms in the naive way. And what he means by that is you only need that second rule for capture avoiding substitution. So I have to say that this, for me, was a block for many years on being able to understand what Barendrecht was doing in his book. I couldn't understand it because I didn't actually figure out that he was kind of like waving his hands and doing some magic on terms, and that substitution wasn't what it really is. And this is sensible in the mathematical context, but it's what I like to think of is it sweeps a huge amount of computational detail under the rug. But fortunately, De Broglie indices have the same effect, even if it makes terms harder to read. So we'll see them later. Now, what time is it? 2:30 about? Maybe I can move this.
Probably about 20 minutes.
Yeah, 20 minutes. All right, so we can do I could be annotating my notes by using annotate. Oh, that's kind of cool. Geez, this is exactly what I've been wanting. Okay. So the eta rule is that the term that looks like this, lambda x dot m applied to x, can be reduced through this eta reduction to just m. So m, because, and that is though if x is not in the free variables of m. Now, see, this is a case where for Barendrecht, he wouldn't really need this side convention because this is bound. So we know that that x is different from every other variable that occurs. And so he can just kind of willy-nilly do eta reduction without any issue. Okay. No, how do I get out of that annotate now? Is there a hand here? Mouse. Okay. Wow, this is a huge breakthrough. Okay. So why does this, why should you agree to this? Why does this make sense? And I guess we can prove a little theorem. And we say, suppose that x is not in the free variables of m. So this variable does not occur free in there. Then lambda x, oh no, he still needs the condition. I apologize. Because x in this context, even if x was a different variable from any other free variable, it still could occur in m. So he does need this condition. And so anyway, then what we want to show is lambda x dot m applied to x is beta equals to m. It's beta equivalent. And so now, if you look at this in Barendrecht, he writes down something like, I don't know, in the theory, how does he even do it? He goes in the theory, beta comma ext shows this. Lambda x dot m applied to x is equal to m. So you can put this in here. So he's saying in the theory where you have access to beta reduction and you have extensionality. And so I just say in here, proof by extensionality, we want to show that for every n, this is just, remember, to prove two functions equivalent. How do you do it? You use something called extensionality. And what does that mean? It means if I have two functions and I could magically check that every input if they're applied to the same input, no matter what that input is, if they always produce the same result, then I know those two functions are equivalent. So look at lambda x dot m applied to x applied to n. And we want to prove for arbitrary n that m, that's beta equivalent to m applied to n. So just choose an arbitrary n, and then you get lambda x dot m applied to x applied to n, and that beta reduces to this term, which is take m, which is applied to x, this term, and replace all the free occurrences of x by n. And there's a lemma on page 8 of Hindley and Selden that says, if x is not in the free variables of m, then when I do this, I just get back m. So then this thing here just becomes m applied to n. So we get this, that in one step of beta reduction, this works. So this means that if you know, oh, that's weird. If you accept beta reduction and you accept kind of as like the computation rule, and then if you accept extensionality as the way of showing that two functions are equal, then you have to accept that this must be true. And so if it's true, then it makes perfectly sense to say, look, you're allowed to just write down this complicated term eta reduces to m. Now, eta reduction is can lead to a mess. In the some of you are familiar with the AGDA, or at least have heard of this programming language called AGDA, which is a dependently typed programming language. And what that means is it's also kind of a theorem proof. And in AGDA, you can like turn off or turn on automated eta reductions in their evaluator. And so often, I'm on the AGDA mailing list, even though I've never really used it. And I look at what stuff that comes up there, and I don't know, not that much comes up. But almost every time somebody's trying to learn the system and they can't get something obvious to prove, people say, oh, turn off eta reduction and it might work. And so, I mean, it leads to complications. But it's true. Okay, so the relation eta, the eta relation is a subset of lambda cross lambda. It's a set of terms that look like this, paired with a set of terms that look like this, as long as x is not in the free variables of m. So that's the relation that relates terms that look like this to terms that look like this. And now this, I'm going through the 3 steps that are standard in Barendrecht for doing this. Instead of doing that k step relation, he defines the lambda compatible step relation, 1-step relation as follows. He says, look, if mn is in this eta relation, then we'll say that m arrow, and there's a little eta under there, goes to n. And if m goes to n by eta, then you can plug any term z, apply z to m, and that goes to z applied to n. And if m goes to n under eta reduction, then you can plug any term on the right, and you can wrap lambdas around anything if you want to, as long as it's got the same variable, x. So that's kind of like the 1-step eta reduction. And now you could look at any big term and you could say, oh, here's a step of eta. I want to simplify something over here. somewhere in the term, in this big term, you've got a subterm that looks like this, and or I'm sorry, that looks like this, and you go like, oh, I just want to replace it by m. And so now you can do that anywhere in a big term. And then the eta, the reflexive transitive closure. Now this is where in Peirce's way, we built that beta sub k relation. And then where did it go? No, it's not above that. Where is it? Ah, here. We built this, goes in k steps, and then we said, okay, and if there's some k, then you get the star. And here we just kind of build the star directly by defining a relation that says, if m eta reduces to n, then we'll say that m eta reduces to n in 0 or more steps. And if m eta reduces to n, everybody eta reduces to themselves in 0 or more steps. The star should be interpreted as in 0 or more steps, m eta reduces to itself. And this is reflexive, adding the fact that it's a reflexive. And here's how you add the transitive part. You say, oh, and by the way, if m eta reduces to n, and that's a star, and n eta reduces to L, and that's a star, then m can eta reduce directly to L. And then on top of this, we can define what it means for things to be eta equal. That should not be an alpha, that should be an eta. This one should be up, draw. That should be an eta under there, not an alpha. So if m eta reduces to n in 0 or more steps, then m is eta equivalent to n. And if m is eta equivalent to n, then we say it's got to be symmetric. N is eta equivalent to m. And now this might seem odd to people who are looking at this and like following what I'm saying, because I added transitivity up here to the arrow sub eta relation, and yet I have to add transitivity again down here for the equality to go. And so I say m is eta equivalent equals to n, and n is eta equals to L. That implies m is eta equivalent to L. But why do I need that? This was transitive. Well, because we might have like an m, and okay, it's eta equivalent to, let's say, m1. And then, but we could have a backward step of eta equivalence. And we could say, okay, that's eta equivalent to m2. Oh, and then m2 is eta equivalent to m3, and like this. And so you can have them going forwards and backwards because of the symmetry in the equivalence relation, but you don't have that up here. You don't have symmetry in the arrow relation. So an arrow, you can only go in one direction. You know, you could say, oh, m is eta equivalent to some, you know, m1 is 80. And so dot, 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 m sub k. Then you can write m arrow star m sub k. But if you have backwards ones, you can't write the arrow star. It doesn't go in 0 or more steps of forward eta equivalence. It goes in 0 or more steps of forward and backwards eta equivalence. And so Anyway, that's why they have to add transitivity again. Okay, so we have just enough time maybe to, if no one has a question, to kind of look where we're going to go next. And that is to discuss this really important property of a system being Church-Rosser. And so I wrote this here, but you know, in Barendrecht's book, when he talks about the diamond property, he just has an R under here. Oh, and I should say that he doesn't write the transitive closure like this. He writes this like this. He writes this as an arrow with two arrows on the front, labeled by the relation. So we've got R's labeled by the relation beta with a star, and he writes this for the transitive reflexive closure of this. But, oh, I can even write outside. Okay. So the diamond property basically says, look, can you see this out here? Yeah. If I have an M and I can beta reduce in, oh, I should have my star there. But anyway, beta, this is a star, and I'll put the beta under the arrow. Beta reduced to M1. So I've got that. And then I also, though, have, in some number of steps, I can beta reduce to M2. Then the diamond property says there has to be this, this N. N has to exist that this beta reduces to that in some number of steps, as well as this. So even if you diverged in doing some beta reduction, you can always come back together. And so this is called the diamond property. This is the diamond. Mouse. This is the diamond property. Okay. Now, then it says here, a reduction is Church-Rosser if its reflexive transitive closure satisfies the dominant property. And so, of course, what you're going to, realize is that beta reduction satisfies this amazing, wonderful property that if you diverge and then you can come back together. This kind of thing was really important back in when AI was more about production systems than it was about machine learning, and you tried to like encode rules that experts used, but multiple rules could fire, and you wanted not to ever get the case where if rule A, B, and let's say you're running a power plant and you fire the rules during some emergency because it's going to tell you what an expert would do in the emergency. It would be terrible if you fired them in one order and the rule says, flip the switch A to off, and the other rule says, leave the switch A on. That would be bad. That would be a kind of a case where you went down one path and you went down another path, you got to different places, and it leaves you not knowing what to do. The diamond property says, it always converges back together. This is also called confluence. And so we're going to, we're not going to bother with the proof. The proof is extremely technical and it's complicated because when we do a beta reduction, sometimes terms get bigger. And so figuring out what's getting reduced, the measure on what's reducing is really technical and complicated. So, and then here's another thing. If M is equivalent by some relation to N, like let's say beta equivalent to N, then there exists a Z such that they commonly go to Z. They both go to Z in some finite number of steps. So it's possible that this branch and this branch actually are the same, and that M, you're just showing that M is equal to M, like even that's a loop, M is equal to M. Well, then there's a Z. Well, how do you choose Z? Oh, Z is just M. What if M is different from N? Well, then you're in a situation like you got something like M1 and M2, but the diamond property says since you came from a common source, you can always find this Z that you can get back to. And that means that if you have a Church-Rosser relation, a transitive reflexive reclosure of a relation that's Church-Rosser, if N is in normal form of M, then M goes to N. So, okay, it's not this N. If you have if there is any normal form, so, this could keep branching back, but there's always a way to get back to the normal form. And you can also use this to prove that at most one normal form exists for each term. So that's the one that you really like, okay? And so it's normalizing, but some branches might go, like there might be an omega in this term, and I can keep going, I can keep following omega down, and I get back to, like I get to M2 again. Well, but look, if I get to M2 again, since M2 goes to N, I could still go back over here. But, maybe it's something even worse. Like there are other terms that grow bigger and bigger and bigger and bigger, but it doesn't matter. This theorem proving the Church-Rosser means you always come back. You can always get back to a common term by beta reduction. So that is a pretty astounding property of the lambda calculus. And we'll talk about that more next time. And then I think, we might go into do a little bit more with fixed points. But, oh, and don't forget to open that thing that Keegan sent you to. It's pretty cool. The Lambda evaluator. But I was going to say, we'll talk maybe a little bit more about fixed points, but I think, without proving it, just showing the Church-Rosser property is probably enough. So I guess that's the end. Any questions? All right. Well, thank you all for coming.
Sir.
Yeah.
Thank you.
All right. No questions. Bye. I'm going to upload this lecture and the notes.